So before I start giving my talk, which is on number fields, I try to recollect what yesterday Raman was trying to explain. Basically, people were interested in solving equations, and this has been a very good old ancient practice. So one can see the traces of such intellectual pursuits being carried out in Greek times. The Indians also have done commendable work in this regard. I can very confidently say that Bhaskara did this. So what they were trying to, in some sense, was that to understand how geometry and then arithmetic can be connected. So it is in this light the whole saga of arithmetic practiced by the ancient mathematicians until to the modern time stands tall. So let us see how we are into this state from those mundane beginnings. Okay. So I titled my talks. In fact, when I said that we need to look at these things, luckily for me, the Raman was very much available. Otherwise, he could have been here today, but for the same reason, he is in Bangalore. Right now, they are holding the workshop over there to commemorate birth anniversary of Ramanujan. But anyway, he did a good job in giving an expository account of what some of these problems of arithmetic and geometry are in terms of the number fields. Okay, so let me pitch it. Yesterday, Raman was in fact was trying to give you a very vivid picture about how these numbers come into play in giving out the geometric rigor. So let me see how I can develop further some of those great ideas. Okay, what are number fields anyway? Okay. So if you ask a simple question about what number fields are, one can also put it this way: what are number sets? Because for mathematics, this is very important. What are number sets? Okay, that's how we abstract everything in terms of set theory. So for us, number sets, the best thing is integers, and then we have rationals. So, and then reals we have C. So these are the most basic and familiar objects as number sets. Okay, one should be familiar with them. Okay, if I say set of integers, integers are the ones coming from this set, and then rationals, which are fractions. So they cook up from, you can pick a pair of integers, and then you have a rational. And likewise, you can look at reals. Ultimately, it is R. So any real number, I mean, so it gets abstracted from, again, these two number sets. So I have real numbers, and then I have complexes. Okay, how did we arrive at all these things? See, starting from integers, then into rationals, reals, and then complex. How did we make this passage? Okay, it was basically the arithmetic that necessitated us. Okay, when I start looking at them and then performing some basic arithmetic operations, you were comfortable to some extent with integers, and then soon you realize that integers are not going to help anymore. And then, so you are into a bigger basket or a bastion where rationals come to fore. Okay, I think wind may be creating some problem. Yeah. Oh, there are. This is a usual scene for me. That's why I keep my lecture hall open. So that's how we have rationals, and then reals, and then complexes. Let me see how we graduate ourselves from integers to all these things. Then what is number field? See, to me, the first thing that I look at them is, because I can naturally perform these operations, addition and multiplication for integers, so I look at this ring. I'm a little bit now pick up some of these things because we are familiar with this. So look at this ring. Okay. I simultaneously perform the operations of addition and multiplication on these integers, and then I get a very, very nice structure known as an algebraic structure called ring. So this ring is the first example, and from there I abstract them. For example, I look for Q plus and then dot. Okay. Now from ring, I get a ring again. Okay, and now this is much more than that. It is much more than that. In fact, it is a field. What do you mean by that? It's not only a ring, it's a field, in the sense every non-zero rational has a multiplicative inverse. Field in the sense every non-zero rational has a multiplicative inverse. So this is very important, especially when you want to solve equations. Because when you are solving equations, quite natural that you may have to perform both the operations simultaneously. Okay, if I can do with one operation with ease, the same thing should be ensured with the other operation as well. And that's why a field is the most accommodative algebraic system in which you can perform these operations very freely, and so that you are comfortable in solving equations. Yesterday Raman was trying to tell that if x square minus 1 is the equation that you want to solve, okay, you can look for solutions in integers, and also you can look for solutions in rationals, and also you can look for solutions in reals. That's the idea that we need to look upon. It's okay. Now, yeah, that's right. Now, as a subfield, I go one step further. As a subfield, okay, Q is the smallest subfield of C. So my R is a field, a real field. C is a field of complexes, and now I have a tower of fields as a subset of R, then as a subset of C. If I look at all those things, Q is the smallest subfield of C, and in between you have R, which is also a subfield of C, and now I want an extension to these number sets, okay, which have very nice structures like a ring structure. Okay, if I take Q plus dot as a ring, I want to see this as a number field. How do I extend this? How did you do this? See, from integers you came to rationals. Now from rationals, where do I go? Because ultimately I need to look at this. So from here I will go next stage, then here, then arrive at R, then continue this journey, and then arrive at C. How do I do these things? Because when you develop a real number system, when you define this real number system, real numbers, We know that every real number is a limiting sequence of rationals. So if I have a real number x, I can cook up a sequence of rationals, okay, a sequence of rationals, set of natural numbers, sequence of rationals such that limit of such sequence will be x. So I get my real numbers. So there is a clear way of landing into from one domain to the another domain through some processes. These processes are limiting processes is calculus actually. Okay, it's nothing to do with your arithmetic. Okay, but as it is, if I say Pn upon Qn, where Pn's and Qn's are integers, then Pn upon Qn is an arithmetic operation. It's a division operation. I get Pn upon Qn because this is arithmetic. I have limiting process. That operation is nothing to do with arithmetic operation. It's basically a calculus process. What is happening is I am looking at the proximities. I keep on looking at x. If my x is root 2, I look for P1 upon Q1, P2 upon Q2, etc., etc., Pn upon Qn, etc., etc. And at each stage, I want to check, okay, I want to see what is this distance. At each stage, for each k. And ultimately what I want is, I want this to go to 0. So if that happens, I have approximated root 2 as some fraction close to that. So that's calculus. Now look at these things. Basically, if I choose arbitrarily an integer, so let d be an integer, a square free. That was the first shock that we get. Root 2 is the first irrational that these people confronted with. So you generalize this too. If my d is an integer, square free, see, need not be, say for example, it can be positive square free. Take this, like your 2, square free, positive. So your d could be root 2, d could be root 3, d could be, it should be square free. Why it should be? If it is square, what will happen? So that's the thing. So if this is square free, they were looking at extensions for these number fields in this form. So the q is extended to q root d. So it starts from that. For every d, I can cook up a field like this. So this is algebra, extension field, index of this set, isn't it? So as a vector space over Q, it's a quadratic extension. Algebraic extension is quadratic. That's why these number fields are called quadratic number fields. So for each such a d, I have my number field. This is a number field. For each such d. And now, if you recollect what Raman was trying to tell yesterday, okay, what was that cyclotomy? What is this cyclotomy business? For a while I digress a bit and I looked at this S1. What is this S1? Yesterday, Raman was describing this S1 as set of all ordered pairs in R2 such that it satisfies an equation. This is a very well-known description about S1, a unit circle in the plane having a polynomial expression of this type, where f of xy is x square. So you can define algebraically all such geometric objects. Alright? So I have my S1. I need to connect these two things with arithmetic and geometry. Is there any way of doing it? Can we generalize this further to something like a quadratic form? Look at these things. This is a quadratic form in two variables where a, b and c are numbers. C are some constants. So I have my fxy. So if I choose my a and c in such a way that a and c are equal and equal to 1, and b is 0, I am getting something like x square plus y square. I choose my a 0, 1, c 1, b 0. So for such constants, I am trying to reflect these things. Okay? And now, so with this digression, what can be seen? So Fermat was looking at these problems. They were known as the Day-2016 problems. Because so it was around 300 BC, 3rd century BC. So the people in Alexandria, Day-2016, was interested in solving such equations, more general for integer solutions, even for rationals. So when Fermat gets the translated works of Day-2016 by Bechet, looks at these equations, and therefore that's how you see that Fermat's last theorem coming up. They call it as a Fermat curve only, because these are curves. So in algebraic sense, they are called as algebraic curves. And Fermat's curve was something like your x raised to n plus y raised to n is equals to 1. So x raised to n plus y raised to n is equals to 1 is a Fermat curve of degree n. This is a Fermat curve of degree 2. But otherwise, the Pythagoras theorem was the geometric beginning for these things. What was the Pythagoras? Pythagoras, you'll have to be very careful with these notations. They call this as homogeneous forms. The degree is same. They use big X, big Y, big Z. When they write curves, they write little x, little y. So these notations are very funny. Okay? And so they write x by z as little x, y by z as little y. Then you get this translation. Little x square plus y square is equals to 1. So that is what is the homogeneity? The homogeneity is the degree is same. So you have dehomogenized that one. So the homogeneity on one hand you have, and then you dehomogenize these things, you get an affine curve like this. X square plus y square is equals to 1. That is your usual analytic geometric way of representing any geometric objects in terms of an algebraic equation like this. So what is this actually? This is x upon z, y upon z, z upon z is 1. So any coordinates that they look at, it's called as a homogeneous coordinates. They write them as, so this is all algebraic geometry things. So your x, y, z as homogeneous coordinates, you reflect this in your Pythagorean triads. What were those Pythagorean triads? For degree 2, 3, 4, 5. Alright? So, that was the first equation that Fermat looked at it and then tried to generalize this to an nth degree expression. So he wanted to see if x raised to n plus y raised to n is equals to d raised to n, where x, y, z are not zero. Non-trivial solutions they want. Trivial solution is okay, but non-trivial. The product should not be zero. So that's the kind of thing Fermat was looking at it. Is it possible to express sum of two cubes as another cube in integers? This was a classic Day-2016 equation. Can you express, can you get a solution to this thing? So this is the thing that he was looking at. But in the melee, what he did was he posed a greater challenge to the people especially to the English mathematicians. So this was around, Fermat was somewhere around 17th century. So he puts up this problem as a challenge, but Euler refers to that problem as Pell's equation. What is this Pell's equation? Euler refers to this equation as Pell's equation, but significantly Pell did not contribute anything to this. Look at this variant form of this equation. X square minus dy square is equals to 1. Look at these things. You graduate from this. This is a nice unit circle. I can give the picture of this on a plane, plotting the graph for these points once I solve this equation. Okay? And we know that you get x is equals to cos theta, y is equals to sin theta, because my r is 1 in this case, and therefore you get, for every theta, there is a point on the unit circle. So there is a solution of this equation. When you plot the graph of this, you get S1. Can I get those things? Can I have a solution set for this, okay, for which xy belonging to R2 such that x square minus dy square is equals to 1. Of course, my d is a square-free integer. So d has to be square-free. If it is square, what will happen? It's very simple. If it is square, what will happen? It gets absorbed into y. But that becomes a square. It's factorable very easily. See, the idea is, if it is square, it becomes, and it's factorable. That's not a big challenge. But the challenge is, I have a surd or irrational coming up. Something that I have under this radical. All right. Now, a quick look at x square minus dy square. This was due to Pell, they said. Pell absolutely did not contribute any significant result towards this. But, Euler, you hold Euler responsible. She named it as Pell equation. Even today it is known as Pell equation. I fell in love with Pell equation when I started doing my research in Day-2016 equations. So I started with those things. That was a great moment for me in my life. It turned my very course of study. So I took to algebraic geometry and many things I studied. So it took me to many places also. That's right. Okay. What is it that you have here? I need to solve this equation. I need to look for a field. What are those field elements? See, once I have a ring elements are called integers. Don't be mistaken with integers in Z. So if I have a ring, and its elements are called ring elements. They are called integers. And in particular, this is a ring, and therefore its elements are called rational integers. We call them as integers because we don't look at, in an abstract sense, a ring and then talk about all those things. But in But in the strict sense of the word, my rational integers means integers that we are familiar with. The members of Z are called rational integers, and any arbitrary ring if you have, they are called integers. And now I have my arbitrary ring. A particular case, if I take Q root D as my R, I must make this into a ring. That's one thing. So I must make this into a ring means I need to define these two operations for these elements. But how does Q root D look like? How does this look like? What is its description? Its elements are of the form U plus V root D such that UV are rationals. This is my ring. UV come from this set, number set. And then my D is square free. D is a square free integer. Need not be positive. It can be negative also. If I take D is equals to -1, I get my Gaussian ring. If I take D is equals to -1, I get my Gaussian ring, which we are all familiar. So Raman was trying to tell you yesterday. So if you look at, because in fact, he was telling that it's a group. So he titled his lecture as Numbers, Curves and Groups. So S1 is a group, isn't it? So there is an algebraic structure here, and therefore, now we look at these things now. So how do you, I can naturally define adding the elements for this under usual addition. You add them separately, component wise, and then that addition is well defined and it's closed. Multiplication, you multiply just as you multiply any two elements, and you see that these two operations are computable, and therefore they satisfy all your ring properties. In fact, this is the number field. It's in fact because my Q is a field. So what are its members? So if I have my, so if U plus V belongs to Q root D, means I call this is an integer. So there's an integer for Q. Alright? So what are those integers? So these are the integers. These are the integers. Now you see that once I have this thing, and then I say that Q root D plus is a group, every element which is an integer should have its inverse. Distinguish the elements, you look at those things. So 0 is of course 0 plus root D times 0. That's my additive identity. And then universe for U plus V root D, I have minus U minus V root D. When you add this with this, I will get 0. And therefore, minus U minus V root D is additive inverse. And therefore, my Q plus will be, in fact, an abelian group. And then multiplication. Binary operation, multiplicative binary operation will also give me not only the ring properties it would satisfy, non-zero integers. Non-zero integers have multiplicative inverses. What are they called? They are called units. In a field, if you have a non-zero element having a multiplicative inverse, then they are called units. So if R is a ring, U in R is non-zero and U in R is non-zero, then and if there exists a V in R such that UV is 1 VU, then we say that U is a unit in R. All right? So, Q root D is a number field. Now, the big question is, what are all the units of a ring? So, I am given a ring. Now, I need to find out what are the units of a ring. That's very interesting because it helps you to solve the equations. What are all the units in a ring? So, if my R is Z, which is a ring, what are all the units of Z? Look at this. This is not a field anymore. That's the first thing that we are stuck with that. Okay? And therefore, what are its units? 1 and minus 1 are the only two non-zero integers which are multiplicative inverses. That's their self-inverses. And therefore, set of all units of R is 1 and then minus 1. 1 and minus 1 under multiplicative binary operation is a group. Therefore, this is isomorphic copy of G modulo 2. A group with two elements. Alright? So it's a group. It's a group under multiplication binary operation. So you collect units of a ring and you look at the binary operation, put a binary operation on those elements. If it forms a group, excellent. This is what you need to see. Because group structure is what? It's a symmetry. If I have some point on the line, R is a group, 0 is the identity, if 1 is this, symmetric point is minus 1. I want that. I want that to happen because my S1 is a group, very symmetric. If P is a point in S1, its antipodal point is its inverse. Symmetry. So S1 is symmetric. R is symmetric. That's why they are all Lie groups. They are not only groups, they are Lie groups. Because there are two things coming up here. One is topology by hindsight, it enters into the realm of our argument for geometry. Because my topology is something to do with connectedness. Because every real number, it could be either a rational or an irrational. That's another thing. Okay? And again, you have a transcendental kind of things. Okay? These intricacies have to be seen very clearly. And they look at this number field. They caught hold of this number field. Look at this number field. That's an amazing thing. So you have this, and then look at this Pell equation now. You factor this. How do you split this into 2? X plus y root d into x minus y root d. Right? This is, I take this, x square minus dy square is what? This is x plus root dy into x minus root dy. What are they? They are the integers in Q. This one belong to Q root d. U plus V root d. So they are the members. So now what is it that right hand side you have? You have 1. So I am demanding this to be 1. Alright? Now, associated with a number field, and for every element of this number field, we define a very interesting function called as norm of that element. You define norm of that element. So if alpha is in Q root d, then you define what is alpha. That is alpha is u plus root d v. Alright? You define norm of alpha. Norm of alpha. norm of alpha as u square minus d v square. That is norm. If it is a Gaussian ring, this norm will be u square plus v square. If it is a Gaussian ring, if my d is minus 1, this norm for alpha will be u square plus v square. Look at this geometric way of trying to abstract the ideas. Ultimately, we are dealing with numbers. The solutions are coming up as numbers. They could be rational integers. They could be integers in general, coming from some number field like this. So, it's a parallel equation. If you look at norm and then set it to 1, plus or minus 1, I would say. So, my L of alpha plus or minus 1 would means what? Would means I have my parallel equation for 1. I have a parallel equation for minus 1. This was indeed a great thing that happened. So if I can, so I need to look at the integers of a number field. Integers of a number field. That's one thing. And then define norm for those elements. And then look for units in them. What are all the units of? So if you look at the units, every non-zero alpha is invertible. And therefore, if you solve a parallel equation, you are trying to look at more generally the units, isn't it? So this was a slighter way of looking at in a some weaker sense. Okay, I would put it in a weaker sense. The Fermat's argument of or looking at Pythagorean way of generating an infinitude of Pythagorean triads as solutions to the Pythagorean equation. So this equation admits an infinitude of integer solutions, provided if epsilon is a solution to x square d square is equals to 1, say plus or minus 1. If you take, then rest of the solutions can be expressible as what? U plus v root d as u dash plus v dash root d raised to n. I will say epsilon I'm sorry, let me write down. Okay, I will write down those things. And then, if x prime, y prime are the solutions, are the such that is a solution to parallel equation then epsilon is equals to then all solutions of Pell equation, and all the solutions of Pell equation can be given by x plus y root d is equals to plus or minus epsilon raised to n, where my epsilon is x prime y prime d, a solution of the Pell equation. So I have a Pythagorean translate of Pell. The idea is, if I can generate an infinitude of solutions, okay, means what? Every integer point, that set, zero set is infinite, countable, algebraic. See, an integer in Q root D, okay, when is that it is algebraic, and because all your algebraic numbers are countable, when do you say that this is algebraic? So in this case, you choose, see, for example, you choose Pell equation, you write Pell equation, you write Pell equation, okay, and then substitute for this, look for, because I'm looking at a polynomial now, look at, write u, a is equals to 2u, b is equals to 2v, then see that this equation satisfies px, pu say, px, let me see, x square minus ax plus c plus ax minus c. X square, just check, x square satisfies there are so many satisfies x square minus ax plus c. So you take some alpha in Q root D and see that P alpha is 0 for these values of u and v. So where C is of course where C is C is your norm of alpha, and you write A as in terms of u and v, and then you compute that, that's the polynomial of degree 2 satisfied by alpha, an integer coming from this number field, and therefore this is algebraic. So an integer is algebraic, so if it satisfies some polynomial, a minimal polynomial of degree n, and so you have algebraic integers, and you solve Pell equation, you get all units. So units in the quadratic field, so you look at those things, that will give you units you have addressed, integers being algebraic you have addressed. These are the two things. And then what is root D is doing? So some discriminant has to come up from these quadratic expressions, and therefore basically I was trying to square up the things basically what I want is Pythagoras. X square plus y square must be z square. Okay. If I can square up these things, in what way I am trying to generalize this and then be happy with every integer that I cook up in a most general number field like this, to go with this kind of Pythagorean business is to look at the reminders, possible reminders that the D will have assumed on division by 4. So that is basically, if D is congruent to 1 mod 4, this is one case, and then D congruent to 2 or 3 mod 4 is another. So you dispense with these two things, then you are done. Because D congruent to 0, I am not interested. It is going to be a degenerate, and therefore D congruent to 1 mod 4 or D congruent to 2 or 3 mod 4, you get a suitable lattice with integral base 1 root D for D congruent to 2 or 3 mod 4, and then another integral base 1 half of 1 plus root D or something you will get. That's another integral base, and so then you generate the integer solutions to a Pell equation. Very interesting things happen here. So that's not the scope of my talk, but I can give you a very interesting account of this problem, going back to what they call it in literature as Archimedes problem, of kettle problem for a Diophantine equation. So for a kettle problem for a Diophantine equation like this, so this D is 1, 2 or 3 or 3 mod 4 business. Okay, if you look at all those things, probably there is a tale, a folklore going back to the days of sun god in some island of Sicily. He wants to know that he wants the people, habitats of that place, to know how many cattle are given to them by the sun god. Okay, the only thing that they have the clue about this problem is they can distinguish cattle by the color. That's the only information they have. So if they they look at two cattle, then they can say that they are either same or they are different by the colors. That is the only information they have about it. And then with that information, manually counting them is not possible. It's ruled out. A manual counting of the number of cattle in the flock is ruled out, but this is the cryptic information they have about this whole population. And then they solve this problem, as cattle problem, with the help of this famous Diophantine equation known as Pell equation. Okay, so very interesting. They generate solutions. So for D is equals to 193, if you take, see 193 is congruent to 1 mod 4, then they generate the solutions. So the whole lot of algebraic number theory comes into picture, provides a thorough algorithm to cook up all these solutions. Okay, so based on the arithmetic of the Diophantine problem, namely the Pell equation. Okay, the geometry is that they generate nice surfaces. See, yesterday Raman was stopped at S1. So if you take S1 cross S1, S1 cross S1 is a torus, a two-dimensional simple, closed, compact, closed surface. Okay, and now you can put infinite lattices on them and then get a discretized version of this whole torus. So if you know the arithmetic, you know the geometry of this. So then you have so many things opening up. That's why probably, Ramanujan had this kind of training or not, but certainly he looked at what is very interesting about number fields is continued fractions. So I will end up with this. with this small remark. So you need to look at the continued fractions of these rational numbers. Can you establish a one-to-one correspondence with rationals unto themselves on the real line is one thing. Rationals, a one-to-one correspondence with the rationals on the number line is another thing. The continued fractions will give us a clear way of doing it, and therefore they write down, you take any rational, say for example 15 by 3 is a rational, you write a continued fraction of 15, they end up after some finite stage, because this is rationals. All these rationals you have finite continued fraction expansions, and all irrationals will have infinite continued fraction expansions, okay? And therefore after some stage they become periodic, whether they are rationals of course they end up after finite stage. So irrationals, they become periodic. For example, you are 22 by 7, okay, you write the continued fraction of 22 by 7 as a rational, okay, and then you write some other things irrational, okay, then you see all those continued fractions. So Ramanujan was very much interested in continued fractions to solve some of these problems, okay, for hypergeometric series, Q series kind of things, okay. With this I conclude my talk, and if there are any questions, I'll be very happy to take them. Thank you very much for your patience.